We have already looked at declared distances in a detailed session which covered TORA, TODA, ASDA and LDA. But I think it's important for us to appreciate all the elements of declared distances by doing a worked out example, because only through a tutorial can the concepts be easily understood. So, today we will look at a tutorial to cover this topic. The aim of this exercise is to obtain values or to determine values of some parameters which will help us in obtaining the declared distances. These four parameters are the full strength pavement, as can be seen in the screen. The full strength pavement basically is the length of the pavement which has to be constructed by the airport authorities to enable carrying the load of the aircraft both during takeoff and landing. So, it is a full strength pavement. Then there is also a clearway, which, as you probably remember, is an open area of land under the jurisdiction of the airport authorities or under the control of the airport authorities, which is clear from any obstacles unless they are required for safe and expeditious operation of the aircraft, such as the taxiway lights, runway lights, etc. It is a clear way. So, it is a piece of land which is clear of obstacles, allowing the aircraft to do the climb after liftoff to achieve the obstacle height, and also it can be used for the approach of the aircraft while landing. The clearway, as you can see, is a piece of land which is centered around the pavement or the full strength pavement, wider than the width and of some length CL, which we will determine. There is also a small piece of land within the clearway called as a stopway. Stopway is used only to hold the aircraft when there is a aborted takeoff. It is designed to allow or to contain the aircraft during the accelerate stop maneuver, and therefore, it is used only during emergencies. It has no role to play in the landing. And then we have what is called as a field length. The aircraft takes off from the start, reaches a place where it achieves liftoff, and after liftoff it climbs to clear the obstacle height. So, the total distance from the starting point to the point where it clears the obstacle height is called as the field length. So, in this exercise we will determine how these four parameters are estimated, and then we will see how they are used to arrive at the values of the declared distances. Let us start with some input data. As I mentioned, we are going to take a case, a theoretical case. So, let us assume that the following input data has been specified for a particular aircraft. So, the normal takeoff distance is 2134 meters, also called as LOD, 1 because 1 represents normal takeoff. Then the distance to height 35 feet, called as D35-1, is 2438 meters. The second case is the engine failure case, in which there are two options for the pilot. If the engine failure is detected at the decision speed, the pilot can either continue takeoff or the pilot can decide to abort the takeoff. So, in the engine failure case, when the pilot decides to continue the takeoff, the liftoff distance for this example LOD2 is given as 2500 meters. Notice it is more than 2134 meters because the aircraft has now suffered one engine failure out of its multiple engines. Therefore, the thrust available is less. Therefore, the distance it requires to reach the liftoff speed is more. 2500 is more than 2134. And also, In the same manner, the distance it will require to clear the obstacle height in this case is given as 2774 meters, which is more than the distance in normal takeoff to clear the obstacle height, that is 2438 meters. The next case is an engine failure case where the takeoff is aborted. For this, we have a parameter called as the accelerated stop distance, normally abbreviated as DAS or sometimes ASD. We will use DAS in this tutorial. That distance from start to the place where the aircraft comes to a rest on the ground is 2896 meters. Notice it is more than both the distance to height of 35 feet in normal takeoff as well as the distance to height 35 feet in the case of a one engine inoperative takeoff. And finally, we have a landing case. In normal landing, the stopping distance or the distance from the place where the aircraft achieves obstacle height to the place where it stops is called as a stop distance. That is specified in this example as 1524 meters. If these are the these are the 6 input parameters, our job is to determine the declared distances for this airport. Here is the procedure for estimation. We consider 4 cases as I mentioned. The first is a normal takeoff case. The second is the engine failure takeoff case in which the takeoff is continued. The third is the engine failure aborted takeoff case in which the takeoff is aborted. And fourth is the normal landing case. So, for all these 4 cases, we use the values of the input parameters to follow a particular steps. The first step is to estimate the maximum field length from all the 4 cases. So, we calculate the field length for all these cases and take the maximum of those 4 and specify that as the required field length. Then we take the maximum and the minimum values of the clearway from the first 2 cases, the normal takeoff case and the engine failure continued takeoff case. Clearway, as I mentioned, has no role in normal landing and also it has no role in the case of a engine failure during aborted takeoff. The fourth one is to find out the maximum Fs from first, second and third. Okay. Fs, as I said, is the full strength pavement. So, here also the engine failure aborted takeoff has no role. So, we look at the value of Fs and take the maximum from 1, 2 and 4. And finally, we determine the value of the stopway. After finding the field length, we find the stopway from the engine failure aborted takeoff case. This is the procedure for estimation of all these 4 parameters FL, CL, Fs and SW. Now, let us take an example, but before that let us understand what is exactly meant by normal takeoff. In normal takeoff, the aircraft starts at the beginning of the runway and it achieves liftoff at a distance called as the LOD. So, the aircraft has started from rest and has achieved liftoff at the distance LOD. After liftoff, the aircraft starts climbing and it clears the obstacle height 11 meters or 35 feet. So, the total distance which is from the start of the rolling mission to the clearance of obstacle height is called as the distance to 35 feet in normal takeoff, and the takeoff distance from this particular requirement or TOD1 is considered as 15% extra of this particular distance. So, notice that the takeoff distance is not equal to just the distance which is specified from the start of the roll to the obstacle height clearance. We give a 15% margin. So, this is first of the 4 formulae that we will be utilizing for calculating the FL. The second case is the engine failure case, but in this case the pilot decides to continue takeoff. In this case, the aircraft is at the beginning of the runway and as it travels on the runway for takeoff, it encounters one of the multiple engines failure. Now, in this example, we have shown that the engine failure is detected at the decision speed V. At this point, the pilot has both the choices. One choice is the pilot can continue the takeoff obviously the lift-off distance achieved here will be more than in the normal takeoff case. So, it will travel to this point and achieve lift-off, and after that it will then start climbing, and also the distance required to clear obstacle height will be slightly larger. So, this is called as an engine failure case with the decision to continue takeoff. Please notice, if the engine failure is detected below the speed V1, it will be prudent for the pilot to apply the brakes and abort the takeoff, because the distance required will be lower. Since the aircraft has not yet attained speed V. On the other hand, if the engine failure is detected at speed more than V, more than the decision speed V, it will be prudent for the pilot to continue takeoff, because if you go for accelerated stop, then you are surely going to encounter a situation where you will exceed the runway. If the failure happens at V, you have both the choices, and in this particular case the pilot has decided to continue takeoff. So, the takeoff distance 2 from the second case, TOD2, is just the total distance travelled from the start of the roll to the place where the obstacle height is reached. Okay. So, that is the takeoff distance 2. The next case is when the aircraft starts rolling, again it reaches decision speed V, at which the pilot detects one of the engines to be failed, and now the pilot decides that it will be better for the pilot to decelerate to stop. So, the pilot applies the brakes and the aircraft comes to rest at this particular point. This distance from the starting point to the place where the aircraft comes to rest is called as the accelerate stop distance, DAS. So, the third estimate of the field length FL3 from case number 3 is the accelerate stop distance, and the fourth is normal landing case, in which the aircraft has reached the obstacle height of 15 meters or 50 feet, and from that point the aircraft now is coming into land, achieves touchdown at this particular point and then continues till it stops. This whole distance on the ground from the place where the obstacle height is reached to the stop point is called as the stop distance, SD, and this distance must be 60% of the total landing distance, or in other words, the landing distance is defined as the stopping distance divided by 0.6, and that becomes the fourth estimate of field length FL4. So, summing up, in normal takeoff case, the total distance from starting of the rolling to the obstacle height, that distance multiplied by 1.15 is called as the TOD1. For the engine failure case but continued takeoff, the total distance travelled from the starting point to the obstacle height clearance without any margin is called TOD2. From the third case, the field length is estimated as the accelerate stop distance from the start of the takeoff to the point where the aircraft comes to the rest, and from the normal landing case, the field length is considered to be the stopping distance divided by 0.6 or the landing distance. Now, we have these four estimates of field length from each of the four cases. To determine the required field length or the field length to be considered, we just take the maximum value of all these four and call it as the field length. Okay. So, we determine four field lengths from four cases and then take the maximum of them. Let us see how we can use this in a solved example. So, again we took the normal takeoff case. So, the data given, as I mentioned to you, is that the lift-off distance or the distance to achieve lift-off from start is 2134 meters, shown in the green arrow here. This distance is the lift-off distance, and then there is a distance to 35 feet which is shown in the figure in the black color. So, therefore, what is the value of TOD1? By definition, TOD1 is going to be 15% extra of the distance 35 feet. So, this I would like you to pause the video and do the calculation yourself. It will be 1.15 into 2438, and that value comes out to be 2804 meters. So, this is the first calculation. The field length or the takeoff distance from the normal takeoff case turns out to be 2804 meters. Keep this in your memory and let us move ahead. Now, we look at the second case, the engine failure continued takeoff case. In this case, the data given to us is the liftoff distance is 2500 meters and the distance to 35 feet is 2773 meters. So, if you recall, TOD2 is equal to the D35 and that is going to be 2773 meters. This is our second parameter to be kept in memory. The third case is the engine failure aborted takeoff case. In this particular case, the data says that the accelerated stop distance for this aircraft is 2896 meter and therefore, that itself becomes the third estimate for the field length 2896 meters. This is the third parameter to be remembered. And finally, normal landing is shown in the data as 1524 meters. So, therefore, the field length fourth is going to be the landing distance, which is equal to the stopping distance divided by 0.6. Please calculate the value of this parameter. You will be able to appreciate these things better if you do the calculations yourself and not just look at the screen. So, this is a good time to pause the video and to take out your notebooks and do the calculations. The value of SD is given as 1524, therefore, FL4 is going to be 1524 upon 0.6, which turns out to be 2540 meter. So, this way we have calculated all the 4 values of the takeoff distance or field length from the 4 conditions, which I am going to summarize here. So, TOD1 was 2804 meters, TOD2 was 2773 meters, FL3 was 2896 meters, FL4 was 2540 meters, and now the maximum value of all these 4 parameters has to be considered as the field length. So, that you can see from the 4 figures turns out to be FL3 or 2896 meters. So, with this we have now estimated the field length as 2896 meters. Moving ahead, let us see how we estimate the length of the clearway or CL. Steps in estimation of CL are as follows. We calculate CL1 maximum value of the CL from the first requirement, that is defined as half of the TOD1 minus 1.15 times LOD1. Okay. This is by definition. There is no physics here, it is just by definition. The CL2 max similarly for the engine failure but continued takeoff case is the TOD2 minus the LOD. Here you can notice there is no margin of 15% given. So, with this the third one is the field length minus the accelerated stop distance. So, what we do is we calculate all these 3 parameters and then we take the minimum of all those 3 as the clearway required. So, let us see a solved example for estimation of clearway. Again, in the normal takeoff case, it is given that the liftoff distance is 2134 meters and the distance to 35 feet is 2438 meters. Therefore, the clearway number 1 or clearway maximum clearway from the first case will be half of TOD1 minus 1.15 times LOD1, which will be 1.15 times D35. So, that number comes out to be. So, TOD1 basically is already arrived at from the previous calculations at 1.15 times D35, which we found as 2804 meters. LOD1 is given as 2134, therefore, CL1 max is going to be half of 2804 minus 1.15 times 2134. Please pause the video here and try to calculate the value yourself. The number comes out to be 175.26 or in short 175 meters. So, from the normal takeoff case, we find that the clearway minimum value of the clearway can be 175 meters. Moving on to the next case, which is engine failure continued takeoff case. Here also the data tells us that the the liftoff distance is 2500 meters and the takeoff distance to obstacle height clearance is 2774 meters. The formula is CL2 max is equal to half of TOD2 minus LOD2. So, TOD2 is D32, D35, that is 2774 meters already mentioned, and CL2 max will be half of that number 2774 minus 2500. This number, I would like you to pause the video and calculate yourself. That number turns out to be 137.16 or 137 meters approximately. Now, we know that the CL1 max is 175 meters, we have just now obtained it. CL2 max is 137 meters, and we know that FL is 2896, and also we know that the DAS or the accelerated stop distance is 2896. Therefore, the difference between FL and DAS is going to be 0. So, what we do now is the clear way for this example will be the minimum value of 0, 175 and 137, which is 0. Therefore, in this example there is no clear way length is 0. Going ahead, let us now estimate the full strength pavement. So, there are steps again in full strength pavement estimation. FS1 is obtained as TOR1, which is TOD1 minus the maximum value of the clear way from normal takeoff case. FS2 is equal to takeoff run 2, which is takeoff distance 2 minus CL from case 2 maximum value, and FS4 is going to be the landing distance or SD upon 0.6. So, what we do is we calculate these three values of Fs and then we take the maximum value of these as the field, as the Fs full strength pavement required. Okay. Now, let us do this for the solved example. Again, in normal takeoff case, Fs1 is going to be TOR1, which is TOD1 minus CL max 1. We know that Fs1 is 2804, and we also know that CL1 max is 175. So, Fs1 is going to be the difference of 2804 and 175. Again, pause the video and do the calculations yourself. The number comes out to be 2629 meters. This is one of the three distances which we need to remember as far as the full strength pavement is concerned. Moving ahead, let us look at again the engine failure continued takeoff case. Here Fs2 is equal to TOR2, takeoff run from case 2, which is takeoff distance from case 2 minus CL2 max. Takeoff distance from case 2 is already mentioned as 2774 meters, and the maximum value of the clear way from the second consideration was 137 meters. Therefore, the difference of these gives us Fs equal to 2637 meters. This is the second number which we need to remember. The third number is the normal landing case. Here the stop distance is given in the data as 1524 meters. So, therefore, what we do is we just divide that by 0.6 to get the landing distance, which is also called as Fs4. So, that will be 1524 divided by 0.6. Already we have calculated that, and that number is 2540 meter. So, to estimate the Fs, we now need to look at the three numbers again. Fs1 was found to be 2629 meters, Fs2 was found to be 2637 meters, Fs4 was found to be 2540 meters. We now take the maximum value of all these three parameters, and that is 2637 meters. So, the Fs in this case is going to be 2637 meters. Now, let us look at the last estimation, which is the stopway. For the stopway, the engine failure aborted takeoff case is the only case which matters. So, in the stopway is going to be the accelerated stop distance minus the full strength pavement. So, in the example problem, we have the stopway as DAS minus Fs, which is 2896 is the DAS, and 2637 just now we calculated is the field strength, is the full strength pavement. So, therefore, the stopway is going to be the difference of these two. I will pause here for you to calculate. The value comes to be 259 meters. So, let us sum up in one glance all the calculations. The field length was supposed to be the maximum of the takeoff distance from first and second consideration, the accelerated stop distance and the landing distance, the maximum of these. Okay. So, it was 2804 for TOD1, 2774 for TOD2, 2896 specified as a DAS and 2540 as LD. So, therefore, the value is 2896 meters. The second calculation is for the full strength pavement, which was the maximum of TOR1, TOR2 and LD. So, that is basically maximum of 2629, 2637 and 2540, which is 2637. The third calculation is the stopway, which is the accelerated stop distance minus the full strength pavement, which is maximum of TOR1, TOR2, LD, that is the Fs, and from that you have to take out the value of DAS. So, it comes out to be 259 meters, and finally, we have the clearway, which is the minimum of 3 parameters, the field length minus DAS or CL1 max or CL2 max. So, we know that in this case the field length and DAS are same 2896. So, the difference is 0. So, the minimum of 0, 175 and 137 happens to be 0. So, this way we get the final runway layout. The full strength pavement in this case is 2637 meters, the stopway is 259 meters and the field length, which is also equal to the accelerated stop distance, is 2896 meters. Okay. Now, in this example there is no clearway because the clearway length came out to be 0. Finally, we need to see how these numbers are converted into declared distances. So, the takeoff run available or TORA is going to be the full strength pavement, which is 2637 meters. The takeoff distance available TODA will be the field strength plus the stopway, which is 2896 meters. The accelerated stop distance available ASDA is 2896 meters already given, and finally, the landing distance available will be equal to the full strength pavement, which is 2637 meters. So, we notice in this case that the TORA is equal to the LDA and TODA is equal to ASDA. In other words, for this example, the declared distances are as follows: TORA equal to LDA equal to 2637, stopway is equal to 259, which is not normally specified, but TODA equal to ASDA equal to 2896 meters. Now, how does it help us? It helps us in the following manner. An aircraft at this airport can only be allowed to operate if the takeoff run required and the landing distance required are less than 2637 meters, and the takeoff distance required and the ASD required will be less than 2896 meters. Only in that case we will allow the aircraft to operate from this particular airport. So, this is how the declared distances are estimated and this is how they are utilized in planning of the operations at an airport. I hope with this example, this tutorial, you would have full clarity about declared distances, how they are arrived, the 4 important parameters, the field length, the full strength pavement length, the clearway length and the stopway, and how they are used to arrive at the 4 declared distances. Thank you so much for your attention.